rope on the chemical world's most exclusive club, the elements that hang out on the far right edge of the periodic table, we're talking about the noble gases.
You can think of them as the cool, kind of aloof celebrities of the element world. They are famously unreactive, they're incredibly stable, and honestly, they just don't feel the need to mix with the other elements. So what's their secret? What makes them so special?
So here's our game plan. First, we're going to meet this elite group and figure out the secret to their stability. Then we'll dive into their unique properties, see how they pop up in our daily lives, and finally, check out some of their most surprising and advanced uses in medicine and tech.
Okay, let's start with the guest list. Who exactly is in this exclusive club?
The noble gases make up Group 18. You might also hear it called Group 0, and it's that final column on the periodic table. This VIP section includes helium, neon, argon, krypton, xenon, and the radioactive one, radon.
For the longest time, everyone called them inert gases. Scientists genuinely thought they were completely incapable of forming chemical bonds. Now we know that's not strictly true. You can force some to react under really extreme conditions, but the name noble gases just stuck. It perfectly captures how reluctant they are to engage with other elements.
So what is the secret to their, let's call it, chemical snobbery? Well, it all comes down to their atomic structure, their internal blueprint. The key phrase to remember here is stable electronic configuration. See, in chemistry, stability is the ultimate goal, and that means having a totally full outer shell of electrons. Most elements have to react with others to get there, but the noble gases, they're just born with it.
Let's take helium. It has just 2 electrons, and those 2 electrons perfectly fill its first and only energy shell. It's complete. It has absolutely no reason to react. We call this stable 2-electron setup a duplet.
And the pattern just keeps going with neon. It's got 2 electrons on the inside shell and 8 on its outer shell. Since that second shell can hold a maximum of 8 electrons, it is perfectly full and unbelievably stable.
And yep, same thing is true for argon, with an electron configuration of 2, 8, 8. That outer shell has 8 electrons, a perfect, stable octet. It is completely content all on its own.
So here's the bottom line. Other elements react because they're trying to achieve this stable state by losing, gaining, or sharing electrons. The noble gases are already there. They've basically won the chemical game right from the start, and that's exactly why they don't form bonds.
Okay, so their stability makes them unreactive. But what does that actually mean for their physical properties? What are these elements really like?
Well, at room temperature, they're all colorless, odorless gases. And because the forces between their atoms are incredibly weak, they have extremely low boiling points. But maybe their most unique physical property is that they are monatomic.
So what on earth does monatomic mean? Well, think about gases like oxygen or chlorine. They always travel in pairs, bonded together as diatomic molecules. Noble gas atoms, though, they are so stable and so self-sufficient, they don't even bond with each other. They just exist as single, solitary atoms.
But there are some clear trends within the group. As you move down the column from helium to radon, the atoms get bigger. This creates slightly stronger forces between them, which means you need more energy to boil them. So as a result, their boiling points steadily increase as you go down.
Now for the really fun part. It turns out that being unreactive is kind of a superpower, and it makes these gases incredibly useful in our everyday lives.
I mean, we've all seen helium in action, right? It's way less dense than air, which is why balloons float. But more importantly, unlike hydrogen, it's completely non-flammable. That stability makes it the only safe choice for everything from party balloons to those giant airships.
And who hasn't seen a classic neon sign? When you pass an electric current through neon gas, it glows with that iconic, brilliant red-orange light. It's basically stability in a tube, lighting up our cities. Argon's inertness is just perfect for protecting that super hot tungsten filament inside old-school light bulbs. Without that protective argon atmosphere, the filament would just instantly burn out. The same idea applies to welding, where argon acts as a shield for hot metal so it doesn't react with oxygen.
But their uses go way beyond the everyday. The heavier noble gases have found their way into some seriously high-tech and even life-saving applications.
Okay, this is where it gets really cool. Krypton is used in energy-efficient windows and in delicate lasers for eye surgery. Xenon powers those ultra-bright headlights that just cut through the darkness. And it's even used as a propellant to steer satellites in the vacuum of space.
But here's a truly surprising one. Xenon is also a highly effective anesthetic. Because it's so unreactive, it barely interacts with the body's chemistry, which means it has very few side effects. It's one of the safest options out there for patients during major surgery.
And even radon, the radioactive member of the family, has a critical life-saving job. Its radioactivity, which is dangerous out in nature, can be precisely harnessed and targeted in radiotherapy to destroy cancer cells. That makes it a powerful weapon in the fight against cancer.
So from filling party balloons to fighting deadly diseases, the noble gases prove that sometimes being unreactive is actually the most useful trait of all. Their incredible stability has unlocked technologies we rely on every single day. And it really makes you wonder, what impossible problem will their perfect stability help us solve next?